Welcome to the fifth lecture of EE311. In this part, we will finalize the analysis of common source amplifier, and then we will continue with the common source with degeneration amplifier. In the previous lecture, we finalized the DC analysis, find the small signal parameters, draw the small signal equivalent for the common source amplifier, which is in here, of course. And I told you that we are looking for three important parameters: voltage gain, input resistance, and output resistance. While finding input resistance, you always keep RS out of the expression because RS is out of your control. And in this particular example, finding it is quite easy. Input resistance is just R1 in parallel with R2. But for more complicated cases, what you need to do is, if you're not sure or if you cannot directly see the input resistance, what you should do is apply some test voltage in here, find the current passing through here, and get the ratio as the input resistance. For finding the voltage gain, there is some mathematics involved in here, but basically what we do is we write V out in terms of VGS first, V out in terms of VGS, and then VGS in terms of VS, and we come up with this expression in the previous lecture. So here is a much clear version of this thing. The input output voltage divided by the input voltage gives the gain as this one. And as you may remember, there are some critical outcomes of this expression. First of all, we have a negative sign. This tells us that input and output are out of phase. If you have a sinusoid like this at the input, the output will be reverse of it. There's 180-degree phase shift. So a common source amplifier, I can say that it's an inverting amplifier. That is one of the most important outcomes in here. The other thing is this R1 in parallel with R2 is in fact Rin. So this term, which is less than 1, is in fact Rin divided by Rin plus Rs. So to be able to maximize the gain, you want to make Rin much larger than the source resistance. And I told you that this is consistent with what we have found in the previous lectures for voltage amplifiers. For voltage amplifiers, you want Rin as large as possible. So if you are designing a common source amplifier, then you want to choose R1 and R2 as large as possible. Having resistances like 100 mega ohm, 200 mega ohms or whatever are quite common. In some cases, people are using like giga ohm resistance to make this input resistance much larger than the source resistance, so that they want to minimize the voltage drop across the source resistance. They want to pass most of this source voltage to the amplifier without losing anything in here. And the other thing is, if you choose R1 and R2 very large, then this term can be simplified in this final expression. Keep in mind that R0 is much larger than any discrete resistance available in the circuit. Let's work on this thing a bit more. This Gm is in fact given by the expression 2Kn ID. We find it in the previous lecture, and Kn is in fact mu n cox W over L. So as a designer, if you want to increase the gain, you cannot play with the electromobility, right? Unless you change the temperature significantly. So this is not a controllable variable. Oxide capacitance per unit area, it is set by the foundry. You cannot play with the thickness of the oxide in the MOSFET. So it's out of question. You cannot play with it. All you can do as a designer is playing with W over L ratio of the transistor. You can use larger width transistors to have more GM. That's one option. So one option is using large W over L ratio. The other option is you can play with ID. You can use larger DC bias for the drain current of the transistor. Of course, there are cons and pros. If you increase the DC bias, if you are using large ID current, then it's going to increase your power consumption. The MOSFET will heat up more and it may create a problem, or power consumption itself may increase. If you do not have enough power budget, then that can be a problem. And also remember the DC circuit. So let's go back to DC circuit to remember it in a better way. If I can find it, of course. Yeah, in this DC circuit, if you increase this current to increase the AC gain, then this will result on more potential drop across RD, right? RD is constant because. And if you have more voltage drop across RD, what's going to happen? Drain to source voltage of the transistor has a smaller room then. It's going to get smaller and smaller. But wait a minute, that's a problem because if you decrease drain to source voltage of a transistor too much, then this transistor may get out of saturation because the saturation condition was VDS should be always larger than VGS minus VTN. By increasing this current, you increase the potential drop across RD. VDS is decreasing, which means that your transistor after some point may get out of saturation, may enter into the linear region, and then forget about the small signal analysis. You cannot use this transistor as an amplifier anymore. So you have to be careful with this increasing the gain issue. If you are trying to improve something, you're always sacrificing from something else. That's the nature of analog design. So you have to be careful about your limitations. We will discuss them in more detail later on, but I'm just trying to give you some hint on this. Okay, so let's go back to our analysis. In this expression, you can play with W over L ratio, you can play with ID, or one other option, you can increase this RD resistance, or this one. You can increase the drain resistance, but it has the same effect basically. You can make it large, but then the voltage drop across RD, DC voltage drop across RD is increasing, which may threaten the saturation condition of your transistor. Your transistor may get out of saturation and therefore it may not operate like an amplifier. But basically, if you want a large gain, you have to increase this expression as much as you can as a designer. And the last thing that we have to find is the output resistance. And for finding the output resistance, you are again excluding the RL in here. For finding output resistance, there's an algorithm that you should apply. For Rout, kill all the independent sources. Independent means that it can be AC as well or small signal, but it shouldn't be dependent. And then apply a test voltage Vx at output. Then find Ix passing through Vx, and then Rout will be equal to Vx over Ix. We will use it a lot, so please try to understand this algorithm in here. So let's apply that algorithm. I'm going to kill all the independent sources. When I take a look at this circuit, I see only one independent source. It's a voltage source. So killing means for a voltage source, I need to short it. Let's do it. So this thing is shorted as the first step. And then apply a test voltage at the output. Of course, I have to exclude RL. So this is Vx, this is Ix. And then I need to find Vx over Ix. But in this case, there is some simplification in the circuit. When you short this voltage source in here, what can you say about the gate potential? You don't have any voltage source in here, therefore no current passing through RS or R1 and R2. Therefore, gate voltage is equal to 0. Source voltage is equal to 0. VGS is equal to 0. which means that I don't have any current passing through this dependent current source. It's going to behave like an open circuit. So when you take a look at from here, you see only this resistance and this resistance. So Rout will be equal to, in fact, RD in parallel with R0. So Rout is equal to RD in parallel with R0, which is approximately equal to RD. Okay, we follow an algorithm while doing this thing. In fact, we spend a lot of time for the analysis, but this is for the first time. And for the next circuit, we are going to spend less time because we are learning it for the first time, right? As you solve another example, it's going to get fastened up. And when you take a look at this circuit, you should be able to tell the input resistance and the output resistance and the gain of the circuit without even drawing the small signal model. But be patient. In a couple of lectures, I guess you get that intuition as well. So let's work on another single transistor amplifier, common source with degeneration. In fact, in the previous structure, we used this circuit. Let's remember it first so that we can compare them. Everything is quite similar, right? Up to this point, I'm using the same components, R1, R2, C1, Vs, RD, and then the load, of course. Everything is the same with the previous circuit up to this point. But in here, we had used some bias current and some capacitance. So this was common source, this is common source with degeneration. In the previous circuit, we used this ideal current source, but unfortunately, in reality, when you are designing a circuit, there is no component named as ideal current source. It's not possible, it's not available. Either you are going to make your own current source over there, or you are going to find another way to create this current. So in practice, you won't see this structure at all. Instead, people replace this current source with a resistor. Let's say RS. This circuit is still a common source amplifier. Why? Because take a look at the nodes, drain, gate, and source. Source is AC-wise grounded still. Nothing changed. The only difference is instead of the ideal current source in here, instead of pushing a well-defined current from the drain or source of the transistor, you put a resistor, and this resistor is for resistor biasing. Eventually there will be some DC current passing through here, and the value is set by this RS, RD, R1 and R2. When you take a look at the left circuit, the difference is this R5 resistance. They add an extra resistance between source and the capacitance in here. That's why it's called as common source with degeneration. Still, input node is gate, the same for common source with degeneration. Output is taken from the drain, exactly the same. Input and output positions are not located. But when you take a look at the source, source is not AC-wise grounded. This node is AC-wise grounded, but between AC ground and the source of the transistor, we have an extra resistor. So it's not exactly common source. Source is not grounded, but because of this R5, it's called as common source with degeneration. So let's analyze this circuit. I'm going to erase this part. DC analysis is almost the same. What should I do? The first thing, kill AC sources. And
İlk önce iPhone'unun kilidini açman gerekiyor.
And open isolation and bypass capacitors. Okay, and when we do that, this will be shorted, this is going to be open circuit, this is going to be open circuit, this is going to be open circuit. So the resulting DC equivalent circuit will be this one. You can even show this R5 and R6 as a single resistor with a value of R5 plus R6. Name the nodes, drain, gate, and source. So this is my equivalent circuit. It is almost the same with the common source one. In fact, it's exactly the same with what I have drawn in the previous circuit. So DC-wise, nothing is different. You know, if you choose R1, R2, RD, and RS the same, for example, DC-wise, nothing will change. And then what you need to do is find the quiescent point, ID, VDS for this circuit, and check the operation point, operation region, which means that it should be in saturation, and therefore VGS larger than VTN, VDS larger than VGS minus VTN, when ID is equal to 1/2 Kn VGS minus VTN. And as a next step, find small signal parameters. With the values that you find from DC analysis, you should find R0 as 1 over lambda ID and GM as 2Kn ID. That is what you expect from the DC analysis. You have to prove that the transistor is operating in the proper region first, then find the small signal parameters from the DC operating point of the transistor. It is exactly the same with what we have done in the previous part. The second step, AC analysis. And for the AC analysis, what we should do, let's remember the items. Kill, so this is for small signal or AC analysis. Kill DC sources. Short isolation and bypass capacitors. And replace the transistor with either hybrid pi or T model. Okay, so let's do it. Let's take a look at it. This DC source will be grounded, okay, because it's like you have some supply in here with VDD voltage. And killing a DC source, DC voltage source, means that you are shorting it. So it should be grounded. I'm going to short this one, I'm going to short this one, I'm going to short this one. When I short it, as you see, R6 will disappear in the new circuit. It's going to be shorted, it's not going to be seen in the final small signal equivalent circuit. So let's draw the full system. Sorry for this, I'm trying to find the correct page. We have the voltage source, Vs, the first isolation capacitor is shorted. Then I have R1 and R2. I can draw them as a single resistor with R1 in parallel with R2 resistance. Then we reach the gate of the transistor. I'm going to use this small signal model hybrid pi for the transistor. Use the node names, drain, gate, and source. GM, VGS, R0, source. Now at the source, unfortunately we have that R5 resistance because R5 is not bypassed. Let's check it. As you see, this node is AC wise grounded. So at the source we have this R5 resistance, so I have to keep it there. R5 will be in here. Then C3 is shorted and we have RL, and this will be the output voltage. So this is my small signal equivalent circuit. Small signal equivalent circuit with hybrid pi model. If you use T model, you will find the same result, but maybe I can show it as an exercise later on. I'm seeking for three important parameters. Always keep it in mind. AV, Rin, and Rout. So let's define their location. While finding Rin, always exclude Rs. While finding Rout, always exclude RL. And let's start with Rin calculation. Okay. For Rin calculation, I'm looking from here, and it's obvious it should be R1 in parallel with R2. But no, I cannot say that. It's direct. Yeah, it's going to be directly equal to R1 in parallel with R2. But if you somehow not sure about this result, what you should do is apply a test voltage in here, Vx, pass a current through here, and find the equivalent resistance then by Vx divided by Ix. But if you do that, you only see this R1 in parallel with R2. So Rin is equal to R1 in parallel with R2. Same as common source amplifier. It didn't change significantly, or it didn't change at all. Let's find AV. When finding AV, I told you that you can do it in two steps. You can write first V out divided by VGS, then VGS divided by VS. But our job is not as easy as the previous one because now one end of R0 is not grounded. So this R0 introduces extra loop equation in here. It makes the things a bit complicated. So as a rule of thumb, for Rin and AV calculations, if one end of R0 is not grounded, you can ignore it. This is going to introduce some error in your calculation, but the error is not that significant. Maybe it's like 1% or whatever. And keep in mind that we are engineers, we are not mathematicians. We are not seeking for the most precise mathematical final result. What we are trying to do is we are trying to come up with some estimation in a short time. For more detailed calculation, there are simulation tools, very nice computers. They can find the actual results in higher precision. But you want to get an intuition of the circuit, so you can make some simplifications. So let's write this rule as if one end of R0 is not grounded, if it makes the mathematics complicated, you can ignore R0. So that's what I'm gonna do. I will assume that R0 is not there at all. And this is gonna simplify it. Why? Because then I can write V out directly, right? The whole current is passing through here. V out will be equal to minus GM VGS RD in parallel with RL. So V out can be written as minus GM VGS RD in parallel with RL. Now I need to find VGS. VG is equal to R1 in parallel with R2 divided by R1 in parallel with R2 plus RS times Vs. Why? Because I have a resistive voltage division in here. Gate voltage Vg is equal to this resistance divided by summation of these two resistance times Vs. Maybe I should use a different notation for the sake of simplicity. So let's name it as V signal instead of Vs, because these two nodes may confuse you. Now I need to find Vs. Vs is equal to Gm VGS times R5. Okay, so VGS is equal to Vg minus Vs, and if you calculate it, VGS will be equal to R1 or Rin, let's say Rin plus Rs times V signal times 1 over 1 plus Gm R5. Okay, so the next step, what I need to do is I'm gonna introduce this expression into here. Then I'm gonna find V out divided by V signal. So let's do it. AV V out divided by V signal will be equal to minus Rin divided by Rin plus Rs times Gm Rd in parallel with RL divided by 1 plus Gm R5. So this is AV of common source with degeneration. And when we analyze it, again we have a negative sign. So which means that this is an inverting amplifier. It's because of that negative sign. Again, Rin divided by Rin plus Rs term appears, and to maximize the gain, you want to maximize Rin. You want to make Rin much larger than Rs. So choose R1 and R2 as large as possible to make Rin divided by Rin plus Rs close to 1. And if that is the case, if you're a good designer, if you choose them properly, you can write AV approximately equal to S Gm Rd RL divided by 1 plus Gm R5. And when you compare it with common source amplifier, because of degeneration, you have this extra term. The gain of a common source amplifier is decreased by 1 plus Gm R5. So this is a quite important outcome of this expression. So gain is decreased by 1 plus GM R5 compared to common source amplifier. So you want large gain amplifiers, right? So this is kind of like a bad thing. Your gain is decreased, but still common source with degeneration amplifiers are quite popular. They are used in many different circuits. And what is the reason? What can be the reason? Let's think about it. So let's compare it with the gain expression of common source amplifiers. So this is for common source with degeneration. For common source amplifier, AB was minus GM RD in parallel with RL. So what is the difference? What can be the advantage of using degeneration resistance if you are sacrificing from the gain? Well, the result is quite obvious, I guess. The main reason is this GM is transistor dependent. Remember the gain. Remember the GM value. It is 2K ID in square root, so it is transistor dependent. So that can be a problem. Let's say that you are running an experiment in the lab, and in the lab you design your common source amplifier. You set a gain something like, let's say, 40 volt per volt. You pick up the most nice, let's say, transistor available in the lab, and the circuit runs perfect, very well, but something happens suddenly and the transistor is burned, and you need to replace that transistor from that transistor box. When you take a look at the data sheet of that transistors, unfortunately, there may be some variations, like for BJTs, beta can change between 100 and 300. For MOSFETs also there may be some variations, and this variation may result in a change in the overall gain of your amplifier. So your amplifier gain is quite transistor dependent. But when you use a degeneration resistance, if you choose this term much larger than 1, then this part will be negligible, and these GMs are going to cancel. And because of that, the overall resistance can be written as RD in parallel with RL divided by R5, which is transistor independent. So it's like one advantage and disadvantage. Disadvantage, you sacrifice from the gain, but the advantage is you make a circuit where the gain only depends on RD and RS value or R5 value. It is not transistor dependent. If something happens to your transistor, when you change it, you will still have the same gain. So in terms of that, you have a more stable operation. And also this addition of the degeneration resistance will help you in stability as well, stability of the system. If somehow, let's say that the gate voltage increases or something happens, you apply some feedback in the system, and this feedback helps you to keep your transistor in the correct operation point. We will analyze this thing in more detail through the end of the semester when we are discussing feedback. But let's mention about it very briefly. Because of this additional resistance, for example, let's say that something happened in your circuit and this DC bias increased, right? And because of that, your VGS voltage increases. Increase in VGS voltage means that drain current is increasing. And when drain current increases, the potential drop across R5 increases and suppresses the increase in VGS voltage. So this is somehow like a feedback. Any increase in here is suppressed by the increase in the voltage drop across R5. So stability-wise, common source with degeneration provides a better amplifier. Common source with degeneration provides a better amplifier in terms of transistor independence as well. But what you sacrifice is, of course, the overall gain. Overall gain decreases significantly because of this 1 plus GMR5 term. But still, it's a very useful amplifier and people used a lot. So we find Rin, we find the voltage gain. Voltage gain expression is quite similar to the common source amplifier, but the gain is decreased, of course. It's still an inverting amplifier. And for achieving a larger gain, you need to choose large RD resistance, of course, with this common source with degeneration amplifier. While dealing with this thing, one last thing that we should find is the output resistance. For Rin and AV calculations, you can ignore R0, but for output resistance, you shouldn't ignore it. So I'm gonna do it in here. For ROUT calculation, what you should do is, as an algorithm, kill independent sources. So this is shorted. And do not ignore R0. So remember that for AV and Rin, if R0 complicates the math, what I mean by this, if one end is not grounded, you can ignore it. But never do it for ROUT calculation. It's not allowed because ROUT all depends on R0 value. And apply some Vx potential, find Ix passing through it. So you're going to apply a Vx potential in here, and you will find Ix passing through here. So let's do it. When you short V signal in here, since no current passing in this branch, you don't need to worry about Rs and R1 and R2. You can say that this node is grounded because no current generated across Rs or R1. So Vg is equal to 0. This is source potential, this is gate, and this is drain. And Rout is Vx over Ix. But it's obvious that Rout is, in fact, Rd in parallel with the resistance seen from here. So I can say that this is, in fact, equal to Rd in parallel with, let's say, Rout prime. Let's name it as Rout prime. And let's name the current passing through this branch as Ix prime. This introduces some simplification in the overall mathematics. We are doing some trick in here. You can always solve Rout by Vx divided by Ix, but it's going to be unnecessarily complicated. When we take a look at this schematic, it's obvious that Rout is Rd in parallel with some other resistance. So instead of finding Rout directly, I'm going to find this some other resistance first and then find Rout accordingly. So I define Rout as, or Rout prime as Vx divided by Ix prime. So now let's try to write Vx in terms of Ix prime. Vx is equal to the resistance or voltage drop across R0 and voltage drop across here, right? So let's write them one by one. Vx is equal to R0 times Ix prime minus GMVGS plus the current passing through here is as well Ix prime, because going in this direction and then merging again, Ix prime R5. So this is my first expression. The second one, I need to write VGS, which is VG minus VS, which is, since gate is grounded, AC was grounded, it is minus Vs, which is equal to minus Ix prime R5. So this is my second expression. So when I combine them, if I put this in here, you can find Vx over Ix prime as R0 times 1 plus Gm R5 plus R5. And keep in mind that this thing is in the range of 100 to 200 kilo ohms. You are multiplying it with something larger than 1, definitely. And this is the source degeneration resistance. It's in the range of maybe less than a kilo ohm or something like that in general. So you can approximate this thing as R0 1 plus GMR5. So this is negligible compared to the first term. But this is Arad prime, and overall Arad will be equal to RD in parallel with R0 1 plus GM R5. So we find Arad. And you can say that, again, this RD is a discrete component. The value is in the range of a few kilo ohms. This thing is in the range of maybe like more than 100 kilo ohms. So eventually the output resistance is dominated by the drain resistance. So, most of the time this thing is approximately equal to RD. If you want to set the output resistance of a common source or common source with degeneration amplifier, basically you would choose RD accordingly. But this RD value affects the gain, of course, so you have to like compromise. Like, for large gain, you can use large resistance or large output resistance. You can use large RD value, but this may threaten the operation point of your transistor, or this may, result in some biasing problems. While designing, you have to optimize it accordingly. And at this point, I guess we find both input resistance, output resistance, and the voltage gain for common source and common source with degeneration amplifier. And in the next lecture, we will continue with more discussion on this amplifier type, and then we will start a new single transistor amplifier, which is common gate amplifier.